Ultrasound instrumentation and image acquisition. Special thanks to Chris Fox of UC Irvine for providing many of the images. A fundamental question in the bedside ultrasound literature is how much training do bedside sonographers require? Keeping in mind that the bedside sonographers in point-of-care ultrasound are physicians and not ultrasound technologists. A study in 2009 looked at the results of short-term training of naive physicians in focused general ultrasonography in an intensive care unit. What they did was 8.5 hours of a training program for novice physicians, which consisted of 2.5 hours of lecture and 3 2-hour bedside hands-on sessions with an expert sonographer. For questions of potential therapeutic impact, the residents in this case answered correctly 95% of the time. The resident exams took approximately 37 minutes, plus or minus 39 minutes, and radiology exams, by comparison, took almost 300 minutes with a large standard deviation. Michael Blavis et al. In 2000 looked at lower extremity Doppler for deep venous thrombosis, whether emergency physicians can be both accurate and fast. They provided a standardized training program that consisted of lecture and 30 hands-on proctored examinations. The results showed a 98% correlation with radiology DVT studies, and the average time of the study took approximately 4 minutes. This talk will be speaking about ultrasonography, knobology, and image optimization and acquisition. Knobology is actually a word in Wikipedia. It's known as the study of knobs as they pertain to medical devices such as ultrasound machines. B mode, or 2D ultrasound, stands for two-dimensional ultrasound, or brightness mode. This is the basic mode of gray and white scale that you see here. When you are in any of the other modes, such as M mode, Doppler, color, or a combination of the above, and you want to get back to grayscale, you push the 2D button, and this gets you back to home base. M mode is motion mode. When this button is pushed, the green vector can be placed across the point of interest, and the M mode button is pushed a second time, and everything that's occurring across that green line of interest is displayed over time on the x-axis. In this case, we're seeing evidence of the M mode line through the pleura. When the M mode button is pushed a second time, evidence of sliding can be seen in what we call the seashore sign, or waves coming into the beach. Once the color button is pushed, there are two basic options. The default option is color flow Doppler, as you see here. Blue is flow away from the probe, and red is flow toward the probe. It's important in this mode that the probe be angled, not at 90 degrees to flow, because if there is no flow coming toward or away from the probe, then the Doppler signal is either weak or non-existent. If you remember BART, you can remember that blue is away and red is toward, or BART. The other option under the color button is color power Doppler. Using the soft key under the CPD, or color power Doppler option, you can enter color power Doppler, and what you see is detection of low velocity flow without evidence of direction. Color power Doppler is orange, and it will show you flow qualitatively, but will not provide directional information. This is very useful in low flow situations, for instance, very small capillaries in the skin surface, or in situations such as trying to detect whether there is flow in a testicular torsion. Again, color power Doppler cannot provide information on direction. When the Doppler button is selected, you enter a mode called pulse wave Doppler. Once you push the Doppler button, you can position the gate, the sampling gate, which is the two hatch marks, within the area of interest. You push the Doppler button again, and you enter the screen where you can detect the arterial waveform or the venous waveform. You'll note on the right of each of the screens there's indication of velocity, centimeters per second. This scale goes up to 40. However, if you needed more or less of a scale, you can choose the soft key button underneath the scale selection to change the scale. Also, if you need to move the baseline up or down to be able to see the entire waveform, you may choose the soft key underneath the word line to move the line. If you would like to change the volume, you choose the soft key underneath the microphone to change the volume. If you want to change the sweep speed so that you can see more complexes or fewer complexes on the screen at a time for comparison purposes, you can change the sweep speed. Here you'll see that right now we're in a fast sweep, so we see fewer per screen. When we change to a medium sweep, we see more complexes per screen. And here's the medium sweep. The language of echogenicity is as follows. Hyperechoic indicates objects that are more echogenic than the surrounding tissue. Hypoechoic indicates objects that are less echogenic than surrounding tissue. Anechoic is devoid of echoes and is black. There are different probes with different frequencies. Typically, we have a P21 and an L38 or L25 probe. The higher the frequency of a probe, the better the resolution. However, the higher the frequency, the less penetration. So, it's a trade-off between resolution and depth. If you need to see structures that are deeper than 6 centimeters, you need to choose a lower frequency probe, but you will trade off detail for that choice. The P21 probe is the probe we use to evaluate the heart and the abdominal organs. The linear probe is the probe we choose for very superficial applications such as procedural guidance, evaluation of the thyroid, evaluation of the pleural line, and deep venous thrombosis evaluation. The C60 probe, curvilinear 60 millimeter footprint probe, is a relatively low frequency probe that is used to image the abdomen, often seen in the emergency room. Within the red circle you see Gen, which means general. When you have a probe, there's a range of frequencies, for instance 1 to 5 or 3.5 to 5 megahertz. This is a curvilinear probe. You can tell that from the footprint here. This is a C60 probe. It had a 3.5 to 5 megahertz frequency. When you're in the general setting, you're about in the middle of that frequency. If you use the soft key to change the setting to res or resolution, you're in the higher range of the frequency available to you. So if you have a very thin patient and you want to get more detail, you can use the soft key underneath and push the button until you get res, and you will get a higher resolution picture. If you need more penetration because you have a larger patient, you can push the soft key again to get pen, and this will shift the frequency coming from that probe to a lower frequency, for instance the 3.5, or if it was the P21 probe, to a frequency of about 1 megahertz. Basics of the transducers. For the convex array probe, or the C60 probe, there's a 60 millimeter footprint. The beams of ultrasound come out in the fashion portrayed here. You will get very good focus in the middle range, but you will have scatter at the edges and lose detail. The P21 probe all beams emanate from a single point. You get excellent focus superficially, and you lose detail as the beams spread more deeply. Therefore, when we are looking at an object of interest, we want that object to be centered approximately here in our image. We don't want a lot of wasted space behind it. Linear probe has beams of ultrasound emanating directly out in a linear fashion. You do not lose detail at the edges of the image as you do in the convex and the phased array probe. In general, the detail is about the same from the top to the bottom of the screen. All probes display the returning echoes drawn on the screen at a certain frame rate. The higher the frame rate, the less herky-jerky the image looks. If you look at objects that are in motion, such as the heart, you will want to select a software mode, such as cardiac mode, that has a higher frame rate so that you get a smoother image. When you're looking at the abdomen, it is not important to have a high frame rate, and actually choosing the abdominals presets will give you a better picture. In here, this area of the screen is where you can see what software presets you're in. This software preset is SMP, or small parts. To change the preset, there's a button on the ultrasound machine that is labeled exam. When you choose exam, it will show you the different types of software available to you, and you want to pick the one that's best for the application. For the heart, you choose cardiac. For the abdomen, you choose abdomen. For vascular, you will have a choice of vascular. If you were doing nerve blocks, there's usually a choice for nerve. Every transducer has an orientation marker or an indicator on it. Depends on the brand of ultrasound machine that you're using as to what the indicator appears like. Sometimes it's a bump, sometimes it's a knob, sometimes it's a light. This indicator is lined up with the dot on the screen so that the sonographer can tell left from right, up from down. Some more terminology for image orientation. When we are looking at things in the longitudinal plane, we also call this the sagittal view. When we are looking at a cross-sectional plane, we also refer to this as the transverse view. Remember, the indicator is on one side of the probe. In the sagittal view, by convention, the indicator is towards the head. In the transverse view, by convention, the indicator goes towards the right. If you flip the probe, the image will flip. Here again, in a closer detailed view, you can see the probe, the indicator bump mark towards the head, and the image that you achieve. And the transverse view, towards the right, and the image that you achieve. The transverse view should always appear like a CAT scan, as if you were looking at the patient from the foot towards the head. Coronal is another term that we use to describe a view, a slice from the side of the patient in the mid-axillary area. By convention, the indicator is oriented towards the head. And that matches with the dot on the screen so that we know that this is the diaphragm, this is the liver, and this is the kidney. The dot is towards the head, opposite is towards the feet. There are several system controls you can use to optimize your image. The depth controls give you some choices. If you choose the upper button, you'll see the arrow points towards a more shallow view. Here, the arrow points towards a deeper view. Every machine has a slightly different appearance of the depth button, but in general, if you push the top button, your image will become more shallow, and the bottom button, your image will be deeper. Here's an example of an image that is 22 centimeters deep. There's a lot of wasted real estate behind this image. The object of interest is at the top of the field. It should be centered in the middle according to the area of focus. Here it's moved to 18 centimeters deep and 14 centimeters deep. So now you get much more detail on the object that you're actually trying to evaluate, the liver and the kidney. The other system control that we often adjust is gain. Gain is the strength of returning echoes. People who are new at ultrasound tend to overgain the image and make it too bright. But undergaining the image, making it too dark, can be equally problematic. Gain can be adjusted on the top or bottom half of the screen or all at once. The near gain knob will adjust the gain at the top half of the screen, the far gain at the bottom half of the screen, and the overall gain will adjust everything equally. Here's an example of the far gain being too low. The top is overgained, the bottom is undergained. In this case, you would want to turn up the far gain so that the picture is balanced. Here's an example where the bottom is overgained relative to the top, and the top is undergained. In order to balance it, we would increase the near gain and possibly decrease the far gain. This is an overall gain issue where the entire field is undergained. In this case, you could choose the gain or the overall gain knob and increase the gain equally. Here's an example where the entire field is overgained or snowy. In this case, you would choose the gain button and turn down the gain. Perfect gain top to bottom. This is a great example of the optimal gain, and we often use this view to actually adjust our gain to get us in the right place to start. The kidney and the liver, when they're together, should always appear as such. Here the kidney looks slightly hypoechoic compared to the echogenicity of the liver. In medical renal disease, sometimes the kidneys are more echogenic, but in general, the kidney cortex will appear darker than the parenchyma of the liver. First, we'll talk about attenuation. When sound encounters high attenuating tissue, echoes are diminished posteriorly, and an acoustic shadow will result. Structures such as bone are high attenuating tissues, and the artifact that's created behind them is a shadow. Here's an example of a gallstone. Here you see the echo behind the stone creates a shadow. We have a hyperechoic stone with a shadow behind. That is classic of a high attenuating tissue. Low attenuation is the opposite. When sound encounters low attenuating tissue, the echoes are actually enhanced posteriorly. We call this posterior acoustic enhancement. Sometimes we take advantage of this to be able to visualize anatomy behind fluid-filled structures such as the bladder. Here's an example. With the bladder, when ultrasound beams go through the bladder, the sound is enhanced posteriorly, and you actually get an image that is too bright. Here you can see that the gain in the far field is being adjusted down so that we can actually see what's behind all that hyperechoic artifact. See, the gain there is being adjusted down. Air will create an artifact. We call it dirty shadowing or scattering. When sound encounters air, much of the signal is lost to scatter. Air is a very poor conductor of sound and will usually reflect all of the sound and scatter it, so there is no signal coming back from whatever's behind the air. Here's an example. There's air-filled structure here and behind. We cannot view what's there. Here's another example. We have a bit of the lung covering the apex of the heart, and because of that we see this bright shadow, also known as a dirty shadow, which is created because of air's presence. Oftentimes this can affect our imaging. When the lung gets in the way, we cannot see the heart, and for people who have emphysema or hyperinflated lungs or on mechanical ventilation, we often cannot see their hearts very well. Refraction will appear on your image as an edge artifact. When sound crosses a boundary of tissue with different propagation speeds, refraction is created and creates an edge artifact. The sound will come through the medium 1, enter medium 2. Medium 2 has a different propagation speed and will bend the sound over to the side, which will create a void and a shadow. This is an example of an edge artifact. There is not actually a dark structure on either side of this vessel. This is an artifact due to the bending of sound as it enters from the soft tissue into the liquid. It bends through and creates an edge artifact. Reverberation artifacts appear as recurrent, bright arcs at equidistant intervals from the transducer. Here's an example. There are not stripes throughout this patient's liver. These are reverberation artifacts. Again, these stripes at the top of the screen are not really there. They're artifacts due to reverberation. The mirror image artifact is created when sound glances off of any very high reflecting structure such as the diaphragm or the pericardium. In the case of the liver, the sound glances off the diaphragm and returns to the probe with a slightly longer time of flight because of the glancing off of the diaphragm. Because ultrasound interprets time as depth, the machine misinterprets this as more liver tissue that is further afield and will create a mirror image of the liver on the opposite side of the diaphragm. Here's an example. Liver, diaphragm. Ultrasound glances off of the diaphragm up to the probe with a slight delay. The probe interprets that as a liver on the opposite side of the diaphragm. This will occur when there is air on the opposite side of the diaphragm. If there happened to be fluid on the other side of the diaphragm, the fluid would allow the ultrasound beam to propagate through, and we would be able to see the anechoic fluid on the other side. So the presence of a mirror image artifact is actually indicative of an air-filled lung. In general, when you're acquiring your image, we need to know your anatomy, visualize the anatomy in at least 2 planes so that we can reconstruct it in the 3 dimensions in our heads, define the boundaries, choose the proper transducer and settings, learn the proper windows for visualizing anatomy, maximize your controls such as gain and depth. The typical learning curve is as follows. When we first start to learn ultrasound, it looks like a snowstorm. Not really clear what's going on there, and we get frustrated. Next, we start to learn our anatomy, and our confidence grows. Then, we get a little bit too bold. We start to think we know what we're doing, but with enough experience and mentoring and patience, you can get to the point very quickly where you're quite adept at both acquiring images, interpreting them, and using them in your patient's care.